intensity as the light that is incident on this side. So you only get half of the intensity of the light from here going through. Yes? Now, if you rotate one of them relative to the second one, so that then what will happen is that the amount of the intensity that goes through will depend on the angle. That angle theta is the angle between this transmission axis of the polarizer number 2 and the transmission axis of polarizer number 1. So this one is vertical, this one is at an angle, so that's, that's the angle between them. So if I rotate one of them, then it'll get darker. And when I manage to make the transmission axis of one of them perpendicular to the transmission axis of the other one, so that the angle between them is 90 degrees, cosine of 90 will give me a 0. So at some point, it just gets dark. Like around there. Do you see my face? Not like when it was like this, right? So that's what that thing was about. What were people asking? Who was in charge of this demo?
Were you?
What were they saying? I mean, or what was the comment, or?
You were cool.
Cool. Yeah, it's hard to explain it, I guess, For example, we're going to learn about thin film interference also, coatings that you can put on glasses, and what we're going to be learning there, this is in chapter 35, I think it is. What if you have a material, whatever, an airplane, for example, surface of an airplane, and then let me do this. Well, a chunk of, let's say this is a chunk of glass. Let's make it simpler. Chunk of glass. And you're over here and you're observing. And maybe you have a picture over here. I don't know, the Mona Lisa or something. Behind the glass. So, you have a picture, you frame it, you got glass in front of it, right? And so light comes in and strikes the glass, right? And goes off that way, and sometimes you get a glare, depending on it's like, I gotta look at it from this angle, oh, now I can see it, or, so like at museums, for example, if it's a famous picture, you may have a lot of people watching, but, hey, get out, hey, we have a pandemic, get out. And, and so there may be people in front of you and not allowing you to see it at the right angle. So what you can do is, you want to cut out some of that glare. So you put a thin film on top of this thing. I'm exaggerating the size of it here. But this is a film. It's called a film because it's very thin. This is just usually a few nanometers thick. I mean, 1,000 nanometers, 2,000 nanometers, something like that. And, just a few wavelengths of the light. And so the idea is that you have light coming in, right? And the light reflects from the front surface of the film. But then the rest of the light goes through and then reflects from the back surface of the film, which is now the interface between the film and the glass. And it goes like this, and then it goes like that, right? And if these two beams come together, the question is that bright or is that dark? So what you're doing is you have an original beam of light, with then part of it reflects from the front surface, the rest reflects from the back surface. And what if those two light beams are recombined? And to cut out glare, right, depending on the thickness of this, you can make the some of the, you can cancel out some of the glare. So, but this is on the topic of interference. And so, that'll be chapters 34, 35, and so sometimes, for example, like you have sunglasses and you walk and there's some glare from the pavement or from the floor, and you want to cut out that glare, so you may put some they're called anti-reflective coatings on the glasses to minimize that. Okay, so these are just linear polarizers over here, but you can also control the amount of intensity of light in one component of the electric field versus another one by putting in these thin films and coating them so that you get, let's say, you get rid of the glare. The example that I was thinking of, only because there's a war going on in Europe, right, with an invasion. Let's say this is the ground, right? And here's an airplane flying this way, and it's a spy plane. In other words, they want to go up there and they don't want to be detected by these people here. So these people have maybe a radar system here. They send out radio waves. So the idea is to send out radio waves, in various directions, and then if it hits the plane, it's going to reflect, and then you have maybe a receiver over here. And if this receiver picks up a signal, there's something up there. Let's shoot it down or whatever, right? So this is a spy plane. You usually spy on the enemy, right? But what if you put a coating? I'm exaggerating the film over here in this case, a coating, thin film coating, such that the light comes this way, right? Part of it reflects from the front surface of the film. I'm not being careful with the wavelength over here, but then the rest of it, the rest of the energy, reflects from the back surface of the film. And it reflects so that it comes out like this. You say 180 degrees out of phase. So what will happen when you combine these two waves together? They'll cancel each other out, destructive interference. And then you get nothing over here, and then there's nothing up there. And what's important to know is what is the wavelength of this. Once you figure out this wavelength, then you can figure out how thick you have to make this thing and what the index of refraction of that has to be. The difficult task is to get that information. And usually the big shots, the generals and so on, are the ones who have secret information like that. Right? But there are tactics of getting that information out of them. I'll let you imagine.